Hello everyone and welcome to this presentation. My name is Julio Cesar Carrasquel. I am a researcher and doctoral student at the Higher School of Economics in Moscow, Russia. The talk of today will be about the modeling of trading systems using Petri net extensions. This work has been done under the supervision of my tutor, Professor Irina Domasova, as well as in cooperation with Andrei Rivkin from the Free University of Bolzano in Italy. So, what is this talk about? In this talk, we will see how to use Petri nets and the different extensions to model trading systems. Our idea is that these models can be used as an input for system analysis for model-based validation. However, actually there can be a very interesting reading about this talk. You will see how a very interesting application domain leads the development of a new Petri net formalism, in which we aim to integrate agent on the one hand and data on the other hand related aspects. So these are aspects that so far they have been individually addressed by other extensions of Petri nets. So how we have organized our presentation? In the first part we are going to introduce which is the problem and the research, our research. In the second part, we are going to describe a bit more in detail which are the components and which are the aspects of trading system that we are focusing. Later on, we will discuss the Petri net extensions, how they tackle specific aspects of trading systems when modeling. For example, on the one part, how a Petri net extension models agent aspects, or on the other hand, the management of data. Finally, after having introduced the Petri net extensions, we are going to present a proposal of an integrated extension in which we aim to integrate all these different aspects in just one formalism. Of course, the first thing is that we need to define what is a trading system. Actually, you see in the image the trading floor of the New York Stock Exchange. This is an example of a venue in which agents are gathered and supported by an information system to exchange goods. So a trading system is composed by a set of agents. These agents aim to buy or to sell securities. Securities can be stock of companies. They are supported in the medium by a trading platform. This trading platform receives orders from agents. Agents submit orders in which they indicate what they want to buy or to sell, and also the conditions, at which price, how many stocks of a security, and so on and so forth. So agents can be individual traders, brokers, corporate firms, people. But also they can be pre-programmed robots, so they can be pieces of software with algorithms implemented in such a way to perform machine-to-machine interaction with the platform. So which are the challenges when designing and analyzing these systems? There are agent issues. There is a huge number of participants interacting with the system and also all of them performing some specific behavior. Concurrency is an issue, how the platform is going to concurrently interact with all of these participants. There are data issues. There are market rules, services that need to be implemented on the platform side to how to process these orders from participants, how orders are prioritized, how traders are performed. There is an analysis issue. Actually, the software testing industry argues that it's computationally expensive to keep a constant monitoring of all these aspects in runtime. Let us consider an analysis trend based on event data. The state of the art suggests that rather than to intrusively check the trading platform, it's better to passively analyze recorded behavior of both participants and the platform in network, which are encoded in network messages. Actually, these messages encapsulate all activities from elements of the system. So there are passive testing techniques that take as input such recorded behavior. There have been proposals of passive testing techniques based on machine learning and even using transition systems. Nevertheless, we know that machine learning techniques are typically agnostic to end-to-end processes. They rarely make use of formal models, for example. And we know that transition systems, they cannot capture concurrency. For example, we cannot develop a specification of expected behavior regarding the interaction of traders using these transition systems. It would be a bit complex. Or how to manage data. This is why in our research we propose the use of Petri nets as we know, is a formalism for the analysis of concurrent distributed systems, so transitions can represent system activities, places they can represent buffers, and the tokens can represent resources of the system. And the firing of a transition can consume tokens from the input places and produce tokens in the output places. Why Petri nets? Let us revisit again these challenges or issues regarding agent and data aspects. The first point of Petri nets is that it allows to model concurrency of the different processes of trading systems. Also, as we will see, there are extensions of Petri nets which they come to enrich the formalism, and we can play with notions of data management, for example, how orders are processed, agent behavior, how to model agent behavior and their interaction with the platform. The idea is that in such extensions, as we will present, tokens, they can carry data, so they can be complex data objects, or these tokens, they can be agents themselves, flowing through the platform. There is an analysis aspect. So using these concepts of agents and data in Petri nets, we can use this model for validation techniques. So models that they encapsulate behavior of traders, we can compare them against the communication logs to check difference between real and expected behavior. Having said this, we present the scheme of our research. In the upper part, you see the system, that is, the participants together with the trading platform. The idea is that we are going to model key components of this system, so we are going to have some modeled behavior. Also, we are going to extract behavior regarding the participants and the platform from the communication logs. With both items, modeled behavior, and the logs, we can perform validation techniques. For example, to replay, that is, to the model, the comparison of the models against the execution traces. But actually, we can do much more with the models. We could perform model-based simulation. For example, to set an initial configuration to conduct what-if analysis. We could also perform model verification. For instance, is it true that our agent model, one agent model, holds some expected condition? So far, we have talked very general about what is a trading platform. Now we are going to introduce which are the key components that we care about of the platform. What you see here in the slide is a simplified view of the platform general architecture. First, there is a trading interface which allows participants to log in the platform and to send and to receive trading related messages. For example, to send orders. Actually, in real life, such interface is implemented by the Financial Information Exchange Protocol, and this standard is widely used. For example, systems like NASDAQ or the London Stock Exchange implement such a standard. There are other interfaces, but these ones are more oriented towards reporting and surveillance. So we focus on the trading interface. And why? Again, because this is the interface where agents actively interact. For example, to log in, to log out from the system. And this is managed by a session component in the platform. As I said, it's also the medium where agents send and receive specific trading messages, for example, to submit an orders. And for example, these orders are going to be a posteriori received and managed by an application component. This is other crucial component we focus on, order books. In the platform, order books are priority lists where orders are inserted. There is an order book for each security being traded in the system. So for instance, if there are 300 securities being traded, then there are at least 300 order books. Order books can be divided in two sides, a buy side and a sell side, where respectively buy and sell orders are placed. As we said, it's a priority list, an order book, so it implements what we call presence rules. These rules determine which orders are going to be considered first for trading. Typically, it's considered the price as a priority. That is, buy orders whose price are higher go first. So this can be seen that the platform is prioritizing who is willing to pay more. Like in this example, order 01 is the first buy order with a maximum price 22. On the other side, on the sell side, sell orders whose price are lower go first. So in this other side, the platform gives priority to whom is willing to sell the lowest price. For example, the best order on the sell side is order 06 with a price of 19.8. And then other thing, how trades are executed. Well, the platform will attempt to perform a trade by crossing the first orders of each side, in this case O1 and O6. When and how this can happen? Well, the platform can execute the trade as long as the price of the first buy order, in this case O1, is higher than the price of the first sell order, in this case O6. I mean, in other words, this means that the best buyer is willing to pay at least as much what the seller specified. We see here that this is true for this case. So O1, its price is 22, which is greater than the price of O6, which is 19.8. So how the trade goes out? So order O1 wants to buy 4 stocks. So when the trade action is fired, the only one stock of O6 will be taken, and the quantities of both orders are decreased. So O1 still will stand as the first buy order because it has still 3 stocks to buy. But O6 will be erased because it has accomplished the selling of 1 stock. In short words, this is how the trade mechanism works in the platform. Now we move to explain how different PetriNet extensions can model different aspects of trading systems. First, we present the use of colored PetriNets. What you see here in the slide, it's a CPM just focusing on the application component. That is, how the platform manages orders in order books, and how it executes trades, as we explained before. So as we know, in CPMs, tokens can represent data tuples. So we can model elements like orders or order books. So for instance, order books can be modeled as 2 list tokens. That's how we do it in this model. The only token in place OB, as we see here, represents the buy side of an order book, whereas the only token in place OS represents the sell side of an order book, of the same order book. Actually, you can see that such representation would allow us to include as many order books as we want without increasing the model structure. Other thing to point out from CPNs is this ability to use an inscription language to specify how objects are manipulated. So exploiting this, we can create functions like, for example, the performance of a order insertion in order books. You can see here in the image how the buy rank function is taking as a parameter a data tuple representing the order and the list representing the buy side of the order book in such a way to insert such a tuple in the list. Also, we can take the first element from each list token to perform trades, as we depict here. Again, so the trade transition will be enabled to fire just provided that the price of the first buy order, in this case P, is greater than the price of the first sell order, in this case P2. So we can see how CPNs can be used to specify this expected functioning of the system regarding the data management. But what about the dynamic modeling of agents? How we can represent this, the dynamic interaction of agents with this platform? Let us quickly recall the interaction flow between traders and the platform. So which are the synchronization points? So first, agents start by logging in the platform, exchanging messages with the session component. So then agents go online, and this is the point where agents receive and send specific trading information, such as send orders or receive trades. Finally, once they have finalized their activities, they go offline. So for such interaction, we consider nested PetriNets. In nested PetriNets, there is a system net which represents an environment, and tokens have associated inner PetriNets. So these tokens can be seen as agents whose behavior are represented by such inner PetriNets. In this example, we are considering the connection management, just what I explained it now. And here tokens are traders. The places of the system net represent the connection status of traders, and the transitions represent the activities performed to change these states. And for instance, an agent can execute an individual init action. So we hear in this example how it moves the firing of the init transition, and it changes the local status of the agent. Then once it's ready to log in, that is in that agent there is a token in place ready, it is fired a login action, and this is going to be in synchronization with the system net. So in nested patterns, this is possible because login activities in the system, both in the system net and in the net token, are labeled with the same synchronization label. So after the simultaneous fading, what happens? So the agent moves the internal status online, and also the system net, it's moving that token representing that agent to the online place in the system net. Of course, once online the agent, we assume that it could have some more behavior specified. Here we don't put it for simplification, but we assume that there could be more activities that it could carry out. And eventually the agent could disconnect, so as we depict here, by a simultaneous firing with the system net. However, let us move a step back. So here the limitation of Petri nets is how the system net and the net token can share data. So how is it possible that the net token, the workflow representing the behavior of this agent, is going to send data, for example, objects to the system net? Because actually we need to describe this, for instance, how orders are sent to the platform, and then also how the system responds back to the agents. We resort to the pioneering concept of DBNets proposed by Montali and Rifkin, where a relational database is integrated in the PetriNet formalism. I'll explain with this example how such integration database plus PetriNet works. So we have a relational database, a set of records. Also there are view places. So these view places, they have attached queries. In this example, this query retrieves all buy orders trading securities SEC1. So what is going to happen is that this view place is going to be populated with copies of such orders. DBNets also have, for example, actions to update the database state. So for example, here we could update an order in the database that is consumed in the PetriNet. So here we could change the status of such order to active. So this is somehow to virtually indicate that now the order is placed in the order book. I mean, by changing such a state, such attribute of the order. So actually these notions of database and queries are an alternative that we can consider. So using this idea of database, agents, net tokens, and a trading platform, a system net, could share data. So for instance, each result of a query answer, like we see here, could be a section of an order book. But the problem is that according to DBNets, each query is assigned to a place and not to a token. So you see here that if we would like to have more order books in our model, like we had with CPNs, we would need to increase the model structure more places. And instead, we would like to maintain such an idea of having least tokens, like we did with CPNs. Finally, we are going to present our proposal. This is our attempt to combine all these requirements to make holistic models of trading systems in such a way that they can be useful for validation of both aspects, agents, and data. So let us review. First, we would like to maintain the idea of CPNs, where each pair of tokens is an order book. So for example, like we showed before with this fragment of CPNs, the token in place OB is the buy side of an order book, and the token in place OS is the sell side of the order book. So doing like that, let us borrow now the idea of a global database. So we ask, what if the actual content of such lists, that is the orders, is actually stored not in the net, but in the database, and instead that the tokens in the colored net could have pointers, so reference to the data that it actually stores, but is in the database. In that way, net tokens, so in this case, in our domain, the traders could access to the content of such list tokens by having also reference to the data in the database. So in this example, the system net would be divided in two parts. So as we see in the right, so there is a part managing agents, another part managing the data. And in short, in the overall proposal, we are combining colored nets and nested nets with the inclusion of a database like in DBNets, but with the idea that queries are on tokens, so we can manage many order book lists. And in this way, also we address the problem that how net tokens can send data and receive data with the system net. This is an example about the idea of references. So in P1 we see an order, so a local order. And in P2 we see two tokens representing the buy sides of order books. The goal here is to include the order token which wants to buy a security SEC1 in place P1 to the list of buy orders stored in the database, which are referenced by token with query Q1 in place P2. Why that one? Because that one is the buy side of an order book for trading securities Sec1. Let us consider first the binding. So first the input expression from place P1 to T3 is assigned with the order token values. Then the input arc expression from P2 to T3 is assigned with the query result of reference token Q1, as we see. You see here that the variable OB is assigned with a sorted tuple of tuples, representing the data that is the list of orders that retrieves the query Q1. And finally, the output arc expression T3P2 is binded with the result of adding to such a list of the query Q1 the order token that is incoming from the input place P1. So if we consider the firing of T3 on token consumption, the token from P1 will be consumed, as well as the list that was stored in the database. So the data referenced by such query Q1. And the data is erased from the database actually. So the data is actually consumed. Notice that we know still by the binding who was the reference token that brought such list to the net level. So in token production, we see how the local data token is passed from the net to the database and is now referenced properly by the query Q1. This reference mechanism, so it could be our potential to allow us to exploit a lot of conceptual abstractions for trading system models. So for example, very interesting is how we could represent with our proposal the behavior of agents in net tokens. So in this example so this is the inner Petri net of a trader, we can see three important parts. So first, the local resources the agent has. And this is similar to CPNs. So we have local data tokens. And these tokens can be, for example, the stock portfolio of the agent, the capital he has, all private attributes of the token. Of course, there is a control flow backbone which orchestrates the agent behavior, what the agent will do. Finally, also there are references. So this will be the looks that the agent has to different data in the database. So we can talk, having said that, we can talk about agent behavior driven by local resources. For example, how an agent may submit to the database orders but the money the agent has. This is an example as we show here in this model. Or instead, in this picture, you can see an example of agent behavior driven by referenced resources. That is, by global resources shared with other agents or the platform. For instance, whenever the platform performs a trade, it could be inserted a trade notification in the database. And eventually, this could be read by the agent using this notion of references in such a way that he will invoke an action to update his local portfolio upon the notification of such trade. Of course, it's also straightforward to implement the same management of order submissions and execution of trades like we did with CPNs, but with the difference, as we have said, that now these orders are going to be stored in the database and they are going to be referenced by the tokens in the platform. So we are concluding our talk. At the moment, we are working in the formalization of this proposal. And as for the future, after having such formalization, our next steps will focus on how to exploit it for the validation phase. Thanks a lot for your attention. So feedbacks and comments are greatly welcome. And please do not hesitate to contact us for any other doubt or any other comment. Thanks a lot.